Chemistry is the study of matter in terms of its composition, structure, properties, and the transformations it undergoes. The subject is concerned with how substances are formed, how they interact, and how they can be changed into other substances. It is a central science because it links together the physical sciences with the life sciences and applied disciplines such as medicine and engineering. Chemists rely on the scientific method, formulating hypotheses, designing experiments, interpreting data, and developing theories to explain observations. These investigations are approached from three perspectives: the macroscopic domain, which deals with phenomena observable by the senses; the microscopic domain, which concerns atoms, molecules, and subatomic particles; and the symbolic domain, which includes equations, formulas, and models that represent matter and its transformations. Matter is defined as anything that has mass and occupies space. The fundamental unit of matter is the atom, the smallest particle of an element that retains its chemical identity and can participate in combinations with other atoms. Atoms often combine to form molecules, which are discrete groups of atoms held together by chemical bonds. Matter is usually encountered in three familiar physical states: solids, which have definite shape and volume; liquids, which have definite volume, but take the shape of their container; and gases, which have neither definite shape nor definite volume. A fourth state, plasma, occurs under conditions of very high temperature and consists of ionized gas particles. In everyday conditions, most matter is not pure, but a mixture. Mixtures consist of two or more types of matter present together in variable proportions. If the composition is not uniform throughout, it is a heterogeneous mixture, such as granite or salad. If the composition is uniform at every point, it is a homogeneous mixture, also called a solution, such as air or seawater. Pure substances contain only one type of matter. They may be elements, which cannot be broken down into simpler substances by chemical means, or compounds, which are composed of two or more types of atoms, chemically combined in fixed ratios. Each substance can be characterized by its physical and chemical properties. Physical properties include features such as hardness, melting point, boiling point, density, and color. These can often be observed without altering the identity of the substance. Physical changes such as melting ice into liquid water involve alterations in form or state, but not in chemical composition. Chemical properties such as flammability, acidity, or reactivity with oxygen describe the potential of a substance to undergo changes that transform it into a different substance. Chemical changes involve the breaking and forming of bonds, producing substances with new compositions and properties. For example, the rusting of iron produces hydrated iron oxides, which differ chemically and physically from metallic iron. Properties of matter can be categorized as extensive or intensive. Extensive properties depend on the quantity of matter, such as mass, volume, or total heat content. For instance, doubling the amount of water doubles its mass and volume. Intensive properties are independent of the amount present and include density, temperature, and boiling point. The density of gold remains constant, whether there is a gram of it or a kilogram. Similarly, the temperature of a body of water does not depend on its volume, but on the average kinetic energy of its particles. Heat is extensive because it scales with the amount of substance, whereas temperature is intensive because it reflects the state of the particles regardless of sample size. Quantitative study of matter requires measurements. A measurement consists of a numerical value, a unit, and an associated uncertainty. Scientific work relies on the International System of Units, abbreviated SI. This system is based on fundamental units, such as the meter for length, the kilogram for mass, and the second for time, as well as derived units, such as the liter for volume, and the kilogram per cubic meter for density. Prefixes extend the range of these units to very large and very small scales. A microsecond represents 10 to the negative 6 seconds, while a megahertz represents 10 to the power of 6 hertz. This allows convenient expression of both atomic scale quantities and astronomical magnitudes. There is a distinction between defined quantities, which are exact by definition, such as 1 inch equaling 2.54 centimeters, and measured quantities, which carry some degree of uncertainty. This uncertainty is expressed through significant figures, which indicate the reliability of the digits reported. When performing calculations, the uncertainty of the result is determined by the uncertainties of the quantities used. Precision refers to the degree of reproducibility among repeated measurements, while accuracy refers to how close a measurement is to the accepted or true value. A set of measurements can be precise without being accurate, or accurate without being precise. Both qualities are important in scientific work, but they serve different purposes. Measurements frequently need to be converted into different units, depending on context. This is done through dimensional analysis, also known as the factor label method. In this approach, units are treated as algebraic factors that can cancel, ensuring consistency and correctness in conversions. For example, converting 10 miles into kilometers involves multiplying by the factor 1.609 kilometers per mile, yielding 16.09 kilometers. This same method applies not only to simple conversions, but also to more complex calculations, such as determining density, speed, or energy by combining measured quantities according to their mathematical relationships. The concept of atoms can be traced back to ancient Greece, where it was proposed that matter is composed of indivisible particles. In the early 19th century, Dalton formalized this idea into a scientific theory, suggesting that each element consists of a unique type of atom that differs from atoms of all other elements in its properties. Dalton also proposed that atoms of different elements combine in small, whole number ratios to form compounds, and that samples of a given compound always have the same ratio of elements by mass. Furthermore, when two elements form more than one compound, the masses of one element that combine with a fixed mass of the other are in small whole number ratios, an observation known as the law of multiple proportions. These ideas supported the law of conservation of mass, which states that during any chemical change, atoms are neither created nor destroyed, but simply rearranged. Experimental discoveries in the late 19th and early 20th centuries revealed details of atomic structure. Thomson's cathode ray tube experiments demonstrated the existence of negatively charged particles, later named electrons. Millikan's oil drop experiment established that the electron carries a fundamental unit of negative charge. Rutherford's gold foil experiment showed that atoms are mostly empty space, but contain a tiny, dense, positively charged nucleus. Within this nucleus, protons were identified as positively charged particles. Chadwick's work later revealed the presence of neutrons, neutral particles that contribute mass but no charge. Soddy introduced the concept of isotopes, demonstrating that atoms of the same element can have identical numbers of protons but differ in the number of neutrons, leading to variations in mass. The atom can be described as a nucleus composed of protons and neutrons, surrounded by electrons moving in regions of space. The nucleus is about 100,000 times smaller in diameter than the atom itself, yet it contains nearly all of the atom's mass. Atomic masses are measured in atomic mass units, abbreviated AMU. One atomic mass unit is defined as 1/12 of the mass of a carbon-12 atom, which is equal to 1.6605 times 10 to the negative 24 grams. Protons have a mass of approximately 1.0073 atomic mass units and a positive charge of +1. Neutrons have a mass of about 1.0087 atomic mass units and no charge. Electrons are much lighter, with a mass of only 0.00055 atomic mass units and a negative charge of -1. The atomic number, symbolized as Z, is defined as the number of protons in the nucleus, and it uniquely identifies an element. The mass number is the sum of protons and neutrons in the nucleus. A neutral atom has equal numbers of protons and electrons. Isotopes of a given element have the same atomic number but different mass numbers. For example, carbon has isotopes with mass numbers of 12, 13, and 14. The chemical behavior of isotopes is nearly identical, since it depends primarily on the number of protons and electrons. The atomic mass of an element as listed on the periodic table is a weighted average of the masses of all its naturally occurring isotopes. Chemical symbols provide shorthand notation for elements. These are composed of 1, 2, or occasionally 3 letters, the first of which is capitalized. Chemical formulas describe the composition of compounds. A molecular formula indicates the actual number of each type of atom in a molecule. An empirical formula gives the simplest whole number ratio of atoms in a compound. A structural formula shows how atoms are connected within the molecule. Models such as ball and stick or space-filling representations can illustrate three-dimensional arrangements of atoms. Compounds with the same molecular formula but different connectivity of atoms are known as isomers. The organization of elements into the periodic table arose from the discovery of repeating patterns in their properties. In the modern periodic table, elements are arranged by increasing atomic number in horizontal rows, called periods, and vertical columns called groups. Elements in the same group exhibit similar chemical behaviors due to similarities in their electron configurations. The groups are numbered 1 through 18. Group 1 elements are the alkali metals, Group 2 the alkaline earth metals, Group 15 the pnictogens, Group 16 the chalcogens, Group 17 the halogens, and Group 18 the noble gases. Elements are further categorized as metals, nonmetals, or metalloids, and also as main group elements, transition metals, or intertransition metals. Chemical bonding involves the transfer or sharing of electrons between atoms. Metals, especially those in groups 1 and 2, tend to lose electrons to achieve the same number of electrons as the nearest preceding noble gas. This produces positively charged ions, or cations. Nonmetals, particularly those in groups 16 and 17, tend to gain electrons until they match the electron count of the next noble gas, producing negatively charged ions, or anions. Nitrogen and phosphorus, in group 15, can also form negative ions by gaining 3 electrons. Ions can be monatomic, consisting of a single atom, or polyatomic, consisting of multiple atoms bonded together that carry an overall charge. Ionic compounds consist of cations and anions held together by electrostatic attraction. These generally form between metals and nonmetals, producing crystalline solids with high melting points. Compounds consisting of neutral molecules instead of ions are covalent compounds, formed when atoms, usually nonmetals, share electrons to achieve stable electron arrangements. Examples of covalent compounds include water, carbon dioxide, and methane. Naming compounds requires standardized rules. Binary ionic compounds consist of a metal cation and a nonmetal anion. The cation name is written first, followed by the nonmetal, with its ending changed to ID. For instance, K2O is named potassium oxide. When a metal forms more than one type of ion, Roman numerals indicate the cation's charge, such as iron 2 chloride for FeCl2 and iron 3 chloride for FeCl3. Many compounds contain polyatomic ions, groups of atoms with a collective charge, such as sulfate, nitrate, and ammonium, which must be memorized for correct naming. Molecular compounds, usually composed of two nonmetals, often form multiple combinations. For this reason, prefixes are used to indicate the number of atoms of each element. For example, SF6 is sulfur hexafluoride, while N2O4 is dinitrogen tetroxide. Acids are another important class of compounds. Binary acids consist of hydrogen and one other nonmetal. Their names begin with the prefix hydro, change the anion ending from "ide" to "ike", and add the word acid, giving hydrochloric acid for HCl. Oxyacids contain hydrogen, oxygen, and another element. Their names depend on the suffix of the anion. Anions ending in "ate" give acids ending in "ike", as in H2CO3, carbonic acid, while anions ending in "ite" give acids ending in OS, as in H2SO3, sulfurous acid. The formula mass of a substance is determined by summing the average atomic masses of all the atoms shown in its chemical formula. The result is expressed in atomic mass units. For covalent compounds, this same value is often referred to as the molecular mass, since it represents the mass of a single molecule. Because atoms and molecules are far too small to measure individually on a practical scale, chemists use a counting unit called the mole to represent large numbers of these particles. 1 mole contains exactly 6.022 times 10 to the 23rd entities, a constant known as Avogadro's number. The mass in grams of 1 mole of a substance is its molar mass. By definition, the molar mass in grams per mole has the same numerical value as the formula mass in atomic mass units. For example, a single water molecule has a mass of about 18 atomic mass units, while 1 mole of water molecules has a mass of about 18 grams. The chemical identity of a substance is defined by the types of atoms it contains and the relative numbers of those atoms. In covalent compounds, these are organized as molecules, whereas in ionic compounds, they are arranged as ions in a lattice. One way to analyze the composition of a compound is through percent composition, which expresses the mass percentage of each element present in the compound. This is often determined experimentally and can be used to establish the empirical formula, which shows the simplest whole number ratio of atoms in the substance. By comparing the empirical formula mass to the measured molar mass, the molecular formula can be derived. For instance, a compound with the empirical formula CH2 and a molar mass close to 56 grams per mole would have a molecular formula of C4H8. Solutions are homogeneous mixtures in which one or more solutes are dissolved in a solvent. A solvent is the component present in the greatest amount, and solutes are the substances present in smaller amounts. If water is the solvent, the solution is described as aqueous. The concentration of a solution is a measure of the relative quantity of solute, compared to the total solution. One of the most widely used concentration units in chemistry is molarity, defined as the number of moles of solute per liter of solution. For example, a solution containing 0.5 moles of sodium chloride in 1 liter of water has a molarity of 0.5 molar. Concentrations can be adjusted by dilution, which is the process of adding more solvent to reduce solute concentration. The relation between initial and final conditions is expressed in the dilution equation, which states that the product of the initial molarity and volume is equal to the product of the final molarity and volume. Besides molarity, other concentration units are frequently used depending on context. Percent composition by mass is useful for reporting concentrated solutions, such as hydrogen peroxide in household products, which might be labeled as a 3% by mass solution. Percent by volume is common in mixtures of liquids, such as ethanol in alcoholic beverages. In cases where solute amounts are very small, concentrations are expressed in parts per million, ppm, or parts per billion, ppb. These units are especially important in environmental chemistry, medicine, and toxicology. For example, the concentration of lead in drinking water is typically expressed in parts per billion due to the extremely small amounts involved, while air pollutants such as carbon monoxide may be measured in parts per million. Each unit is chosen for clarity and practicality in its particular scientific or industrial application. Chemical equations provide a concise way of representing chemical and physical changes. In such equations, the formulas of the substances that react, called reactants, are written on the left side of an arrow, while the formulas of the newly formed substances, called products, are written on the right. Integer coefficients placed before each formula indicate the relative numbers of atoms, molecules, or formula units that participate in the reaction. A properly balanced chemical equation ensures that the number of atoms of each element is the same on both sides, reflecting the law of conservation of mass. In reactions carried out in aqueous solution, equations can be written at varying levels of detail. A molecular equation shows the overall reaction with complete chemical formulas. A complete ionic equation separates all strong electrolytes into their constituent ions. And a net ionic equation shows only the species that actually undergo change, omitting spectator ions. Reactions can be grouped into categories based on recurring patterns of behavior. Precipitation reactions occur when two aqueous solutions are mixed and an insoluble solid forms, such as when solutions of silver nitrate and sodium chloride produce solid silver chloride. Acid-base reactions involve the transfer of hydrogen ions, often between an acid and a base, as in the neutralization of hydrochloric acid with sodium hydroxide to form water and sodium chloride. Oxidation reduction, or redox, reactions involve changes in oxidation numbers, which correspond to the transfer of electrons. For example, the combustion of hydrogen involves hydrogen being oxidized and oxygen being reduced to form water. For complex redox reactions in solution, the half-reaction method is used, in which the oxidation and reduction processes are written separately and then combined to yield a balanced overall equation. Stoichiometry refers to the quantitative relationships between the amounts of reactants and products in a chemical reaction. These relationships are determined directly from the coefficients in a balanced equation. Each coefficient can be used to derive conversion factors, called stoichiometric factors, that relate moles of one species to moles of another. These factors are the foundation for calculating masses of substances consumed or produced. volumes of gases at defined conditions, or concentrations of solutions involved in reactions. For example, the balanced equation 2, H2 plus O2, arrow 2, H2, O shows that 2 moles of hydrogen gas react with 1 mole of oxygen gas to yield 2 moles of water, providing direct mole ratios for calculations. Not all reactions proceed with the exact stoichiometric amounts of reactants. Often one reactant is present in a smaller quantity than required to completely react with the others, making it the limiting reactant. The limiting reactant determines the maximum amount of product that can be formed. The predicted amount of product based on stoichiometry is called the theoretical yield, but in practice, reactions often produce less due to side reactions, incomplete reactions, or loss of material during handling. The actual yield is the amount of product obtained experimentally. Percent yield is the ratio of actual yield to theoretical yield, multiplied by 100, and it provides a measure of the efficiency of a reaction. Stoichiometry also underpins quantitative methods of chemical analysis. In titration, a solution of known concentration, called the titrant, is added to a solution containing the analyte until the reaction is complete, usually indicated by a color change of an added indicator. The volume of titrant used, combined with the balanced equation, allows the concentration of the analyte to be calculated. Gravimetric analysis is another approach in which the analyte is converted into a pure, stable compound that can be isolated and weighed. From its measured mass, the amount of analyte present in the original sample is deduced using stoichiometric relationships. Combustion analysis, a specific type of gravimetric method, is used to determine the elemental composition of compounds, particularly organic ones. In this method, a compound is burned in excess oxygen, and the masses of the gaseous products such as carbon dioxide and water are measured. From these data, the amounts of carbon and hydrogen present in the original sample can be calculated. Energy is defined as the capacity to do work or supply heat. Work in this context is the process of applying a force to move matter over a distance. Energy exists in different forms, most commonly kinetic energy and potential energy. Kinetic energy is associated with motion, such as the movement of molecules in a gas, while potential energy is related to position, composition, or condition, such as the energy stored in chemical bonds, or gravitational potential energy due to height. The first law of thermodynamics, also known as the law of conservation of energy, states that energy may be converted from one form to another, but cannot be created or destroyed. The thermal energy of a substance arises from the kinetic energy of its atoms or molecules as they move, vibrate, or rotate. Temperature is an intensive property that measures the average kinetic energy of the particles in matter. When temperature increases, it indicates an increase in this average kinetic energy. Heat, on the other hand, refers to the transfer of thermal energy between two systems at different temperatures, always flowing from the hotter system to the cooler one until thermal equilibrium is reached. Processes that absorb heat from their surroundings are described as endothermic, while processes that release heat are exothermic. The joule, abbreviated J, is the SI unit used for energy, work, and heat. 1 joule is defined as 1 kilogram meter squared per second squared. The ability of a substance to absorb or release heat depends on its physical properties. Heat capacity is the amount of energy required to raise the temperature of an object by 1 degree Celsius. Specific heat capacity, or simply specific heat, is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. The quantity of heat transferred to or from a substance depends directly on its mass, its specific heat, and the temperature change it experiences. For instance, heating a kilogram of liquid water by 10 degrees Celsius requires 41,800 joules of energy, given that the specific heat of water is 4.18 joules per gram per degree Celsius. Calorimetry is the experimental measurement of the heat involved in chemical or physical processes. A calorimeter is an insulated device designed to minimize energy exchange with the surroundings. The simplest type, the coffee cup calorimeter, is used to measure heat changes at constant pressure, typically for reactions in solution. More advanced devices such as bomb calorimeters are designed to measure energy changes during combustion reactions at constant volume. These instruments determine the amount of heat released or absorbed by carefully monitoring temperature changes and using known masses and heat capacities of the system. When a chemical reaction is carried out at constant pressure, and the only work involved is expansion or compression of gases, the heat associated with the process is referred to as the enthalpy change, symbolized as delta H. If the reaction is exothermic, delta H is negative, indicating that heat is released to the surroundings. If the reaction is endothermic, delta H is positive, indicating that heat is absorbed from the surroundings. The value of delta H is proportional to the amount of substance undergoing reaction. The enthalpy change for a forward reaction has the same magnitude but opposite sign as for the reverse reaction. The standard enthalpy of formation, symbolized as delta HF standard, is the enthalpy change that occurs when 1 mole of a compound is formed from its constituent elements in their most stable forms under standard conditions of 1 bar pressure and a temperature of 298.15 Kelvin. These tabulated values allow chemists to calculate enthalpy changes for a wide variety of reactions. Hess's law states that if a reaction can be expressed as the sum of multiple stepwise reactions, the enthalpy change of the overall process is equal to the sum of the enthalpy changes of the individual steps. This principle makes it possible to determine enthalpy changes for reactions that are difficult or impossible to measure directly by combining data from other known reactions. Electromagnetic radiation travels through a vacuum with a constant speed of 2.998 times 10 to the 8th meters per second. This radiation exhibits wave-like properties that can be described in terms of wavelength, symbolized by lambda, and frequency, symbolized by nu. These two quantities are related by the equation c equals lambda times nu, where c is the speed of light. Light is a traveling wave, but waves may also exist as standing waves, which are restricted to specific lengths, demonstrating the concept of quantization. When electromagnetic radiation passes through 2 narrow slits, with separations comparable to its wavelength, an interference pattern is observed, providing evidence of constructive and destructive interference. In addition to wave properties, electromagnetic radiation also behaves as a stream of particles called photons. Each photon has an energy directly proportional to the frequency of the radiation, given by the equation E equals h times nu, where h is Planck's constant. This dual behavior of light as both a wave and a particle is known as wave-particle duality. All types of electromagnetic radiation, from radio waves to gamma rays, share this dual nature, though they interact with matter differently and find different applications. Radiation can be produced by exciting matter, for example by heating. The resulting emission can either be continuous, such as the black body radiation from the sun, or discrete, such as the line spectra produced by atoms like hydrogen. The hydrogen emission spectrum provided critical evidence that atomic energy levels are quantized, and its pattern could be expressed mathematically by the Rydberg formula. At the end of the 19th century, several phenomena could not be explained by classical mechanics and electromagnetism. These included the blackbody radiation problem, the photoelectric effect, and the existence of discrete atomic spectra. Their resolution required the development of quantum theory. Bohr incorporated Planck's and Einstein's ideas into a model of the hydrogen atom. He proposed that the electron moves in circular orbits around the nucleus, with each orbit corresponding to a specific energy level. Electrons are restricted to these quantized orbits, and transitions between them involve the absorption or emission of photons, whose energy equals the difference between the two orbit energies. When an electron drops from a higher orbit to a lower one, energy is emitted as light. When it is promoted to a higher orbit, energy must be absorbed. The Bohr model accurately described the hydrogen spectrum and provided a way to calculate the energies and radii of electron orbits in one-electron systems. Further developments showed that electrons could not be fully described as particles moving along exact paths. Instead, they display both particle and wave properties. According to quantum mechanics, the behavior of an electron is described by a wave function, symbolized by psi. The square of the wave function gives the probability of finding an electron in a particular region of space. These probability regions are called orbitals, and they represent the most likely locations of electrons in an atom. Orbitals are defined by quantum numbers. The principal quantum number, n, is a positive integer and indicates both the relative energy of the orbital and the average distance of the electron from the nucleus. All orbitals with the same value of n belong to the same electron shell. The angular momentum quantum number, L, can take values from 0 to n-1 and determines the shape of the orbital. Orbitals with the same values of n and L form a subshell. The magnetic quantum number, m sub L, has integer values from negative L to positive L, and specifies the orientation of the orbital in space. Each electron also has a spin quantum number, m sub S, with a value of plus 1/2 or minus 1/2. No two electrons in the same atom can share the same set of four quantum numbers, a principle known as the Pauli exclusion principle. The filling of orbitals follows an order determined by their relative energies. Starting from lowest energy, orbitals are filled in the sequence 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. Hund's rule states that electrons occupy orbitals of equal energy singly with parallel spins before pairing occurs. These rules, along with the exclusion principle, allow the construction of electron configurations and orbital diagrams for atoms. The valence electrons, which are those in the outermost orbitals, are primarily responsible for chemical behavior. Elements within the same group of the periodic table have similar valence configurations, explaining their similar properties. Some deviations from the expected filling order occur, particularly when half-filled or fully filled subshells provide extra stability, as in the cases of chromium and copper. The periodic table can be divided into categories based on the orbital that receives the last electron. The main group elements involve the filling of s and p orbitals. Transition metals involve the filling of d orbitals, and the inner transition metals involve the filling of f orbitals. Elements involve the filling of f orbitals. The arrangement of electrons in orbitals explains periodic trends in the properties of elements. the covalent radius generally increases down a group because higher values of n correspond to larger orbitals. Across a period, the radius decreases because the effective nuclear charge increases, pulling the electrons closer to the nucleus. When atoms form ions, the size changes significantly. Cations are smaller than their parent atoms because electrons are lost while the nuclear charge remains constant, pulling the remaining electrons more strongly. Anions are larger than their parent atoms because the addition of electrons increases electron repulsion while the nuclear charge remains the same. Ionization energy is the energy required to remove an electron from a gaseous atom. It decreases down a group because outer electrons are farther from the nucleus and easier to remove. It increases across a period because the increasing nuclear charge holds the electrons more tightly. Electron affinity is the energy change when a gaseous atom gains an electron. Negative values indicate exothermic processes, meaning energy is released when the electron is added. In general, electron affinity becomes more negative across a period, as added electrons occupy lower energy orbitals closer to the nucleus. Moving down a group, electron affinity becomes less negative as added electrons occupy higher energy orbitals farther from the nucleus. Both ionization energy and electron affinity show exceptions when subshells are half-filled or completely filled, since these configurations are particularly stable. Atoms often achieve stability by either losing or gaining electrons, forming ions with noble gas like electron configurations. Metals, especially those in groups 1 and 2, readily lose their outermost electrons to form cations with positive charges that correspond to the number of electrons lost. Nonmetals tend to gain electrons until their valence shells are filled, forming anions with negative charges that reflect the number of electrons gained. The resulting ions adopt stable configurations that resemble those of the nearest noble gases. Covalent bonding arises when atoms share electrons, with the shared electron pair attracted simultaneously by the nuclei of both atoms. In a purely covalent bond, electrons are shared equally between identical atoms. In polar covalent bonds, electrons are shared unequally because one atom exerts a greater attraction for the bonding pair. This ability to attract shared electrons is quantified as electronegativity. The difference in electronegativity values between two bonded atoms indicates the degree of polarity. If the difference is negligible, the bond is essentially nonpolar. A significant difference produces polarity, and a very large difference results in ionic bonding, which is best viewed as electron transfer rather than sharing. Lewis symbols provide a way to represent the valence electrons of atoms and ions, while Lewis structures extend this to molecules and polyatomic ions by showing bonding and non-bonding electron pairs. Most Lewis structures follow the octet rule, where atoms are surrounded by 8 valence electrons. Hydrogen is the major exception, requiring only 2 electrons to be stable. Some compounds are exceptions in other ways. Free radicals are molecules with an odd number of electrons, leading to unpaired electrons. Electron-deficient molecules, such as boron trifluoride, contain fewer than 8 electrons around the central atom. Hypervalent molecules, such as phosphorus pentachloride and sulfur hexafluoride, contain more than 8 electrons around the central atom, possible for atoms in the third period and beyond due to available d orbitals. To evaluate competing Lewis structures, formal charges are assigned by dividing bonding electrons evenly between the 2 atoms involved. The best structure is the one in which atoms bear the smallest formal charges and negative charges, when present, reside on the more electronegative atoms. In cases where multiple valid Lewis structures exist with the same arrangement of atoms, but different distributions of electrons, resonance occurs. The true electron distribution is best described as a resonance hybrid, in which electrons are delocalized across the structure rather than confined to one form. Bond strength can be quantified by bond dissociation energy, the energy required to break 1 mole of bonds in the gas phase. Single bonds are generally weaker than double or triple bonds between the same atoms, as multiple bonds involve greater electron sharing and stronger attraction between nuclei and electrons. Reaction enthalpies can be estimated by comparing the total bond energies of bonds broken with the total bond energies of bonds formed. In ionic compounds, the strength of bonding is reflected in lattice energy, the energy needed to separate 1 mole of solid ionic compound into gaseous ions. Lattice energy is larger for ions with higher charges and smaller ionic radii. The Born-Haber cycle is a method used to calculate lattice energies by summing the enthalpy changes for all steps involved in forming the ionic compound from its constituent elements. Molecular shapes can be predicted using the valence shell electron pair repulsion theory, abbreviated VSEPR. This model states that regions of electron density around a central atom, whether bonding pairs or lone pairs, arrange themselves to minimize repulsions. The resulting geometry of these regions is the electron pair geometry. The actual molecular structure, which describes only the arrangement of atoms, may differ when lone pairs are present. For example, the electron pair geometry of ammonia is tetrahedral, but because one of the positions is occupied by a lone pair, its molecular structure is trigonal pyramidal. Molecular polarity depends on both the polarity of individual bonds and the geometry of the molecule. Each polar bond has a bond dipole moment directed toward the more electronegative atom. If these dipoles add vectorially to produce a net separation of charge, the molecule is polar and will interact with electric fields. If they cancel due to molecular symmetry, the molecule is nonpolar despite having polar bonds. For example, carbon dioxide has 2 polar carbon-oxygen bonds, but its linear geometry causes the dipoles to cancel, making the molecule nonpolar. In contrast, water has 2 polar bonds arranged in a bent geometry, leading to an overall dipole moment and strong polarity. Valence bond theory explains covalent bonding as the result of overlap between 2 atomic orbitals from different atoms. This overlap creates a region of electron density shared between the atoms, forming a covalent bond. When the overlap occurs along the axis directly connecting the 2 nuclei, the bond is called a sigma bond. When the overlap occurs in a way that creates a node along this internuclear axis, the bond is called a pi bond. Sigma bonds are the strongest type of covalent bond because the electron density is concentrated directly between the nuclei, while pi bonds provide additional bonding strength by overlapping orbitals in a side-by-side manner. The concept of hybridization extends valence bond theory by describing how atomic orbitals can mathematically combine to form new hybrid orbitals that better explain molecular geometries. Hybrid orbitals can form sigma bonds directed toward other atoms or hold lone pairs of electrons. The type of hybridization is determined by the number of regions of electron density around a central atom. 2 regions result in sp hybridization, associated with linear geometry. 3 regions result in sp2 hybridization, associated with trigonal planar geometry. 4 regions result in sp3 hybridization, associated with tetrahedral geometry. 5 regions produce sp3d hybridization, associated with trigonal bipyramidal geometry. 6 regions correspond to sp3d2 hybridization, associated with octahedral geometry. Pi bonds, in contrast, are always formed from unhybridized p or d orbitals that remain available for side-by-side overlap. When 2 atoms form multiple bonds, the first bond is always a sigma bond, while additional bonds are pi bonds. A double bond consists of 1 sigma bond and 1 pi bond, while a triple bond consists of 1 sigma bond and 2 pi bonds. Because pi bonds require parallel alignment of unhybridized orbitals, resonance can occur when more than one valid arrangement of pi bonds is possible. In such cases, the actual electron distribution is delocalized across the structure, producing greater stability than would be achieved by a single resonance form alone. Molecular orbital theory provides an alternative description of bonding by treating electrons as occupying orbitals that extend over the entire molecule rather than being localized between 2 atoms. These molecular orbitals are formed from combinations of atomic wave functions. When atomic orbitals combine in phase, they produce bonding molecular orbitals that increase electron density between nuclei and stabilize the molecule. When they combine out of phase, they produce antibonding molecular orbitals, which have nodes between nuclei and reduce stability. Molecular orbitals that concentrate electron density along the internuclear axis are sigma orbitals, which can be formed from the overlap of s orbitals, or p orbitals aligned end to end. Molecular orbitals formed from the side-by-side overlap of p orbitals are called pi orbitals, with electron density above and below the axis between nuclei. Electrons fill molecular orbitals according to the same principles used for atomic orbitals. They occupy orbitals in order of increasing energy, fill singly before pairing according to Hund's rule, and each orbital can hold a maximum of 2 electrons with opposite spins. By applying molecular orbital theory to diatomic molecules, the bond order can be calculated as 1/2 the difference between the number of electrons in bonding and antibonding orbitals. A positive bond order indicates a stable molecule, while a bond order of 0 indicates instability. One advantage of molecular orbital theory is its ability to predict magnetic behavior. Molecules with unpaired electrons in molecular orbitals are paramagnetic and are attracted to a magnetic field, whereas molecules with all electrons paired are diamagnetic and are weakly repelled by a magnetic field. For example, oxygen gas is paramagnetic because it contains unpaired electrons in degenerate pi-star antibonding orbitals, a property that cannot be explained by Lewis structures or valence bond theory alone. Gases exert pressure, which is defined as force per unit area. In the SI system, pressure is measured in pascals, where 1 pascal equals 1 Newton per square meter. Because this unit is very small, pressure is often expressed in kilopascals, atmospheres, bars, or torr. Standard atmospheric pressure is defined as 1 atmosphere, which is equal to 760 torr, or 101.325 kilopascals. Atmospheric pressure can be measured with a barometer, typically consisting of a column of mercury supported by air pressure. Other types of manometers are used to measure gas pressures in laboratory settings, usually involving the displacement of a liquid column by the gas sample. The behavior of gases can be summarized by several empirical gas laws. Amundsen's law, also called Gay-Lussac's law, states that at constant volume, the pressure of a given amount of gas is directly proportional to its absolute temperature. Charles's law states that at constant pressure, the volume of a gas is directly proportional to its absolute temperature. Boyle's law states that at constant temperature, the volume of a gas is inversely proportional to its pressure. Avogadro's law states that at the same temperature and pressure, equal volumes of gases contain equal numbers of molecules. These relationships are unified in the ideal gas law, expressed as P times Φ equals N times R times T, where P is the pressure, V the volume, N the number of moles, R the gas constant, and T the temperature number of moles of gas, T the temperature in kelvins, and R the gas constant, which has a value of 0.08206 liter atmospheres per mole Kelvin when convenient units are used. The ideal gas law is a versatile tool, allowing calculation of any one property of a gas when the others are known. It can be rearranged to provide equations for gas density and molar mass. For example, the density of a gas can be expressed as P times M divided by R times T, where M is the molar mass. Dalton's law of partial pressures provides a means of describing gas mixtures, stating that the total pressure of a mixture is the sum of the partial pressures of the individual gases. Avogadro's law also allows stoichiometric calculations involving reactions of gases, since equal volumes of gases at the same temperature and pressure contain equal numbers of particles, regardless of identity. The motion of gas molecules explains many macroscopic gas properties. Diffusion is the spontaneous mixing of gas molecules from regions of high concentration to regions of low concentration, driven by random molecular motion. Effusion is a related process in which gas particles escape through a tiny hole into a vacuum. According to Graham's law, the rates of effusion of two gases are inversely proportional to the square roots of their molar masses. Thus, lighter gases effuse more rapidly than heavier gases. For example, hydrogen effuses about 4 times faster than oxygen, because the square root of 32 divided by 2 equals approximately 4. The kinetic molecular theory provides a conceptual framework for understanding ideal gas behavior. It makes several assumptions. Gases are composed of molecules in continuous random motion. The molecules are very small relative to the distances between them, so their individual volumes are negligible. Collisions between molecules and with container walls are perfectly elastic, meaning no energy is lost. And the average kinetic energy of molecules is proportional to the absolute temperature of the gas. The distribution of molecular speeds follows a pattern that broadens and shifts toward higher values as temperature increases. At any given temperature, lighter molecules move faster on average than heavier ones. Real gases deviate from ideal behavior because the assumptions of kinetic molecular theory are not strictly valid. Molecules do occupy finite volumes, and intermolecular forces do exist. These deviations are most pronounced at high pressures, where molecules are forced closer together, and at low temperatures, where intermolecular attractions become significant relative to kinetic energy. Under such conditions, the ideal gas law no longer accurately describes behavior. The van der Waals equation introduces correction terms to account for both the finite size of molecules and the attractive forces between them. This modified equation provides a more accurate description of real gas behavior, bridging the gap between ideal theoretical models and experimental observations. The properties of liquids and solids can be explained using the kinetic molecular theory. In liquids, intermolecular forces hold molecules close together, but the particles still have enough kinetic energy to slide past one another. This gives liquids both definite volume and the ability to flow. In solids, intermolecular forces are even stronger, restricting particles to fixed positions and giving solids both definite shape and volume, The forces responsible for the condensed states of matter are collectively referred to as van der Waals forces. These are electrostatic in nature and vary in strength, depending on the type of interaction. Dipole-dipole forces occur between polar molecules, where the partial positive end of one molecule is attracted to the partial negative end of another. Even non-polar molecules experience London dispersion forces, which arise from temporary fluctuations in electron distribution that induce instantaneous dipoles. These forces increase in strength with increasing molecular size and polarizability. Hydrogen bonding is a particularly strong type of dipole-dipole attraction that occurs when hydrogen is covalently bonded to highly electronegative atoms, such as fluorine, oxygen, or nitrogen. The exposed hydrogen nucleus creates a strong electrostatic attraction with lone pairs on nearby electronegative atoms. The presence and strength of intermolecular forces influence macroscopic properties of liquids. Cohesive forces, which are interactions between like molecules, are responsible for viscosity, the resistance to flow, and for surface tension, the tendency of the liquid surface to behave elastically. Adhesive forces, which are interactions between molecules of a liquid and those of another substance, explain phenomena such as capillary action, in which a liquid rises in a narrow tube against gravity due to the stronger adhesion between liquid and tube walls. Matter changes phase when intermolecular interactions are either overcome or strengthened. Melting, vaporization, and sublimation are endothermic processes because energy must be supplied to separate particles. Freezing, condensation, and deposition are exothermic processes because energy is released as particles come together and intermolecular attractions are established. The temperatures at which phase transitions occur depend on the strengths of the intermolecular forces involved, meaning that substances with stronger attractions melt and boil at higher temperatures. The conditions under which a substance exists as solid, liquid, or gas are summarized in a phase diagram. This diagram plots pressure against temperature and includes curves that represent equilibrium between different phases. The point where all three curves intersect is the triple point, the unique set of conditions under which solid, liquid, and gas can coexist in equilibrium. Below the triple point pressure, the liquid state cannot exist. At the upper end of the liquid-gas curve is the critical point, defined by a critical temperature and pressure beyond which the liquid phase can no longer exist, regardless of how much pressure is applied. Above this point, the substance exists as a supercritical fluid with properties of both liquids and gases. Solids may be crystalline, with a highly ordered internal arrangement, or amorphous, lacking long-range order. Crystalline solids exhibit sharp melting points because all of their structural units experience identical interactions, while amorphous solids soften gradually over a temperature range due to irregularities in bonding. Crystalline solids can be classified into four major types. Ionic solids consist of cations and anions held together by electrostatic forces, producing brittle materials with high melting points. Metallic solids consist of metal atoms whose valence electrons are delocalized, producing conductivity and malleability. Covalent network solids consist of atoms linked by covalent bonds into a continuous structure, as seen in diamond or quartz, and are typically very hard with extremely high melting points. Molecular solids consist of molecules held together by intermolecular forces such as London dispersion, dipole-dipole, or hydrogen bonding. They tend to be softer and have lower melting points. Crystalline solids often contain defects in their regular arrangement. Vacancies occur when particles are missing from lattice sites. Impurities may be present, substituting for atoms in the lattice or occupying spaces between them. These defects can significantly alter the physical properties of solids. For example, adding controlled amounts of impurities to silicon crystals changes their conductivity, enabling their use as semiconductors in electronic devices. The arrangement of particles in crystalline solids can be described using packing models. Metal atoms often pack in arrangements that maximize space efficiency. The two most efficient structures are hexagonal closest packing and cubic closest packing, both achieving about 74% space filling. Other arrangements include body-centered cubic and simple cubic, which are less efficient. Ionic compounds adopt structures in which the larger anions form a lattice framework, and the smaller cations occupy the spaces, or holes, between them. Depending on their size, cations may occupy tetrahedral holes, octahedral holes, or cubic holes. The repeating arrangement of a crystalline solid is described by its unit cell, defined by its dimensions and particle contents. X-ray diffraction is the primary method used to determine unit cell structures and provides precise information on the arrangement of atoms within a crystal lattice. A solution is a homogeneous mixture at the molecular level, formed when two or more substances combine physically. The solvent is the component present in the greatest concentration and defines the physical state of the solution, while the solutes are the other components present in smaller amounts. Depending on the balance of intermolecular forces, solution formation may be endothermic, requiring input of energy, or exothermic, releasing energy. When the interactions between solute and solvent are nearly identical in strength to those within the pure substances, the process is energetically neutral, producing an ideal solution. When substances dissolve in water and yield ions, they are classified as electrolytes. Electrolytes may be ionic compounds that dissociate into cations and anions, or covalent compounds such as acids that react chemically with water to produce ions. The dissolution of ionic compounds is driven by ion-dipole attractions between the ions and polar water molecules, which stabilize the ions in solution. Compounds that ionize completely, such as sodium chloride or strong acids like hydrochloric acid, are strong electrolytes. Weak acids and bases, such as acetic acid or ammonia, ionize only partially and are classified as weak electrolytes. Substances that dissolve without forming ions, such as glucose, are non-electrolytes. The ability of one substance to dissolve in another is expressed as solubility, defined as the maximum concentration of solute that can exist in a solution at equilibrium under given conditions. A saturated solution contains solute at its solubility limit, while a supersaturated solution contains more solute than is stable under those conditions, often leading to precipitation if disturbed. Solubility depends strongly on intermolecular forces. Liquids that dissolve freely in one another are miscible, such as ethanol and water, whereas liquids with negligible mutual solubility, such as oil and water, are immiscible. For most solid solutes, solubility increases with temperature, although there are exceptions. For gases, solubility decreases as temperature rises, because increased kinetic energy allows gas molecules to escape more easily. Gas solubility is directly proportional to its partial pressure above the solution, a relationship described by Henry's law. For example, carbon dioxide is more soluble in soft drinks under high pressures of gas during bottling and escapes rapidly when the pressure is released. Solutions exhibit colligative properties, which depend only on the number of solute particles present and not on their identity. Adding solute lowers the vapor pressure of a solvent, elevates its boiling point, and depresses its freezing point. The magnitude of these changes depends on the total particle concentration, whether the particles are molecules or ions. Ionic solutes may not completely dissociate, so the actual colligative effects observed can be smaller than those predicted by assuming complete dissociation. Osmotic pressure is another colligative property and refers to the pressure needed to prevent the net movement of solvent molecules through a semi-permeable membrane into a solution. Osmosis is critical in many biological systems, such as the regulation of water balance in cells. Colloids are another class of mixtures, consisting of particles dispersed throughout a continuous medium. The dispersed particles are larger than typical solute molecules, but small enough to remain suspended without settling under gravity. They may be solid particles or liquid droplets, and are often stabilized by surface charges that prevent aggregation. Colloids are abundant in natural systems and in technological applications. Examples include milk, fog, and smoke, as well as industrial colloids like paints and gels. Their properties, such as light scattering and the Tyndall effect, distinguish them from true solutions while still sharing many similar behaviors. The rate of a chemical reaction is measured by the change in concentration of reactants, or products, per unit time. For any reaction, the rate can be expressed in terms of the disappearance of reactants or the appearance of products. The stoichiometric coefficients in the balanced chemical equation are used to relate these different rate expressions. For example, in the decomposition of hydrogen peroxide into water and oxygen, the rate of oxygen formation is 1/2 the rate of hydrogen peroxide consumption because of the stoichiometric relationship in the balanced equation. Several factors influence reaction rates. For reactions involving multiple phases, the rate increases with greater surface area contact between reactants. A solid reactant will react more quickly when finely divided into a powder than when in bulk form because of the increased surface exposure. Temperature also strongly affects reaction rates because higher temperatures increase the kinetic energies of molecules, making collisions more frequent and more energetic. Similarly, higher reactant concentrations increase the likelihood of effective collisions, leading to faster reaction rates. Catalysts enhance rates by offering an alternative reaction pathway with a lower activation energy, allowing more collisions to result in product formation without being consumed in the overall reaction. The mathematical form of a rate law, also known as a differential rate law, describes how reaction rate depends on the concentrations of reactants. A general rate law has the form rate equals K times the concentration of A raised to some power times the concentration of B raised to another power, where K is the rate constant. The exponents, called reaction orders, indicate how strongly each concentration affects the overall rate and must be determined experimentally. The overall order of a reaction is the sum of these exponents. Common cases include zero-order reactions, where the rate is independent of concentration, first-order reactions, where the rate is directly proportional to one reactant's concentration, and second-order reactions, where the rate depends on the square of one reactant concentration or on the product of two reactant concentrations. Less commonly, reaction orders may be fractional or negative. Integrated rate laws are derived from differential rate laws and describe how concentrations change over time. Each reaction order produces a different integrated form. Zero-order reactions yield a linear relationship between concentration and time. First-order reactions yield a linear relationship between the natural logarithm of concentration and time. Second-order reactions yield a linear relationship between the reciprocal of concentration and time. These integrated expressions allow the prediction of concentrations at any time during a reaction and are especially useful for determining rate constants from experimental data. The concept of half-life, the time required for the concentration of a reactant to decrease by half, is often used to characterize reaction rates. For zero-order reactions, the half-life depends directly on the initial concentration and decreases as the concentration decreases. For first-order reactions, the half-life is constant and independent of concentration, making this order especially common in radioactive decay processes. For second-order reactions, the half-life is inversely proportional to the concentration, so it becomes shorter at higher concentrations. Reaction rates can be explained by collision theory, which states that molecules must collide with sufficient energy and proper orientation to react. Not all collisions are effective. Only those exceeding a certain activation energy barrier result in products. The Arrhenius equation expresses the temperature dependence of the rate constant. K equals A times E to the power of negative EA over RT, where A is the frequency factor accounting for collision orientation, EA is the activation energy, R is the gas constant, and T is the temperature. As temperature increases, the exponential factor increases, explaining why reaction rates accelerate at higher temperatures. Most reactions proceed through a series of elementary steps, collectively called the reaction mechanism. Each step may involve one molecule, unimolecular, two molecules, bimolecular, or less commonly, three molecules, termolecular, colliding simultaneously. The overall rate of a reaction is controlled by the slowest step in the mechanism, called the rate-determining step. The rate law for an elementary step can be written directly from its molecularity. By comparing the experimentally determined rate law with the rate law predicted by a proposed mechanism, chemists can evaluate whether the mechanism is plausible. Catalysts modify mechanisms by providing lower energy pathways. Homogeneous catalysts are in the same phase as the reactants and typically work by forming intermediate species that react more readily. Heterogeneous catalysts exist in a different phase, often a solid surface that adsorbs reactant molecules, bringing them into proximity and weakening their bonds. Both types of catalysts increase reaction rates without altering the overall thermodynamics or being consumed in the net reaction. A reversible reaction reaches equilibrium when the rates of the forward and reverse reactions become equal. At this point, the concentrations of reactants and products remain constant, though both processes continue at the molecular level. Equilibrium is therefore dynamic rather than static. The state of a reaction mixture at any moment can be described using the reaction quotient, Q. This quantity is calculated in the same way as the equilibrium constant, K, but applies to concentrations at any point in time, not just at equilibrium. If Q is less than K, the forward reaction is favored and the system will shift toward producing more products. If Q is greater than K, the reverse reaction is favored and the system will shift toward producing more reactants. When Q equals K, the system is at equilibrium. Equilibria are classified based on the phases of the components involved. A homogeneous equilibrium involves species that are all in the same phase, such as a mixture of gases or a solution with dissolved ions and molecules. A heterogeneous equilibrium involves species in different phases. For example, the equilibrium between solid calcium carbonate and the gaseous products carbon dioxide and calcium oxide in its thermal decomposition. In equilibrium expressions, only gaseous and aqueous species appear, while pure solids and liquids are omitted because their concentrations are constant. When an equilibrium system is subjected to a disturbance, it responds in a way that counteracts the disturbance, a principle known as Le Chatelier's principle. If the concentration of a reactant is increased, the system shifts in the forward direction to consume some of the added reactant. If the concentration of a product is increased, the system shifts in the reverse direction. Changes in volume and pressure affect equilibria involving gases. Reducing volume, which increases pressure, shifts the equilibrium toward the side with fewer moles of gas, while increasing volume shifts it toward the side with more moles of gas. Changes in temperature alter the value of the equilibrium constant because they change the relative rates of the forward and reverse reactions. If the reaction is exothermic, raising the temperature favors the reverse process. If the reaction is endothermic, raising the temperature favors the forward process. Catalysts, however, do not alter the equilibrium position. They lower the activation energy for both forward and reverse reactions equally, allowing the system to reach equilibrium more quickly without changing the equilibrium composition. Equilibrium constants and concentrations are often determined using quantitative calculations. A systematic approach employs an ICE table, which organizes information about the initial concentrations, the changes in concentration that occur as equilibrium is approached, and the equilibrium concentrations. By substituting these values into the expression for the equilibrium constant, unknown concentrations or the equilibrium constant itself can be calculated. This method is widely applicable and essential for predicting the behavior of chemical systems in equilibrium. A Brønsted-Lowry acid is defined as a species that donates a proton, or hydrogen ion, while a Brønsted-Lowry base is one that accepts a proton. In any acid-base reaction, the acid loses a proton and becomes its conjugate base, while the base gains a proton and becomes its conjugate acid. These conjugate acid-base pairs differ only by the presence or absence of a single proton. Some species are amphiprotic, meaning they can act as either acids or bases depending on the reaction conditions. Water is the most important amphiprotic substance, capable of donating a proton to form hydroxide ions or accepting a proton to form hydronium ions. This dual role allows it to undergo autoionization, represented by the equilibrium 2H2O liquid in equilibrium with H3O plus aqueous plus OH minus aqueous. The equilibrium constant for the autoionization of water is called the ion product of water, Kw, which equals the product of hydronium and hydroxide concentrations. At 25 degrees Celsius, Kw has a value of 1.0 times 10 to the negative 14. This provides the foundation for the pH and pOH scales, which express hydrogen ion and hydroxide ion concentrations on a logarithmic scale. By definition, pH equals the negative logarithm of the hydronium ion concentration, and pOH equals the negative logarithm of the hydroxide ion concentration. Because their product is constant, the sum of pH and pOH is always 14 at 25 degrees Celsius. Solutions with pH less than 7 are acidic. Those with pH greater than 7 are basic, and those with pH equal to 7 are neutral. The strength of an acid or base is quantified by its ionization constant, A strong acid or strong base has a large ionization constant, indicating nearly complete ionization in solution. Weak acids and bases have much smaller constants and only partially ionize. Within a conjugate acid-base pair, there is an inverse relationship between strengths. The stronger the acid, the weaker its conjugate base, and vice versa. In aqueous solution, the leveling effect limits observable strengths. Any acid stronger than hydronium ion will donate protons completely to form hydronium, and any base stronger than hydroxide ion will accept protons completely to form hydroxide. Trends in acid strength can be observed across the periodic table. Among binary compounds of hydrogen, acid strength increases from left to right across a period as the electronegativity of the other element increases, making the bond to hydrogen more polar and easier to break. Acid strength also increases down a group because bond strength decreases, making it easier for the hydrogen to dissociate. Thus, within the halogen series, hydrofluoric acid is weakest, while hydroiodic acid is strongest. In oxyacids, acid strength increases with the oxidation number of the central atom because additional electronegative oxygen atoms draw electron density away from the OH bond, weakening it. For example, sulfurous acid is weaker than sulfuric acid. Acid strength also increases with the electronegativity of the central atom, as in the comparison of selenic acid and sulfuric acid. Salts dissolved in water may also affect acidity or basicity. Cations that are conjugates of weak bases hydrolyze to generate acidic solutions, while anions that are conjugates of weak acids hydrolyze to generate basic solutions. Transition metal cations often form hydrated complexes in which water molecules act as ligands, and the coordinated water can donate protons, giving acidic character to the solution. Polyprotic acids, such as sulfuric acid, carbonic acid, and phosphoric acid, contain more than one ionizable proton. These acids undergo stepwise ionization, each step characterized by a separate equilibrium constant. The first ionization constant is usually much larger than the subsequent ones, reflecting the increasing difficulty of removing additional protons from an increasingly negatively charged species. Because of these differences, equilibrium calculations often treat each step separately with negligible error. Buffer solutions contain significant amounts of a weak acid and its conjugate base, or a weak base, and its conjugate acid. Such solutions resist changes in pH when small amounts of strong acid or strong base are added, because the conjugate pair neutralizes the added species. However, once one component of the pair is consumed, the buffer capacity is exceeded and the solution can no longer resist pH changes effectively. Acid-base titrations provide a means of analyzing unknown concentrations. In a titration, a solution of known concentration is gradually added to a solution of unknown concentration until neutralization is achieved. The titration curve, a plot of pH against the volume of titrant added, provides valuable information about the acid or base under investigation. The shape of the curve varies depending on whether the titration involves a strong or weak acid or base, and whether the acid or base is monoprotic or polyprotic. The point at which neutralization is stoichiometrically complete is the equivalence point. Appropriate indicators are chosen based on the expected pH at this point to signal the completion of the reaction. The equilibrium constant that governs the dissolution or precipitation of a slightly soluble ionic solid is called the solubility product, abbreviated KSP. consider the general equilibrium M(pxq) solid in equilibrium with PMM plus aqueous plus QXN minus aqueous. The corresponding solubility product expression is Ksp equals the concentration of MM plus raised to the power P times the concentration of Xn minus raised to the power Q. The concentrations of pure solids are omitted from equilibrium expressions because their activities are constant. The value of Ksp can be used to calculate the molar solubility of an ionic solid, and conversely, experimental solubility data can be used to determine Ksp values, provided no other significant equilibria complicate the process. The precipitation of a slightly soluble compound depends on the relationship between the reaction quotient Q and Ksp. When Q is less than Ksp, the solution is unsaturated and more solid can dissolve. When Q equals Ksp, the solution is saturated and equilibrium exists between solid and dissolved ions. When Q exceeds Ksp, the solution is supersaturated, and precipitation occurs until Q decreases to equal Ksp. This principle allows prediction of whether a precipitate will form under given conditions, such as when two ionic solutions are mixed. Equilibria can also be described using the Lewis acid-base concept. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. This definition broadens the scope of acid-base chemistry beyond proton transfer. Complex ions exemplify Lewis acid-base adducts. They consist of a central metal ion, acting as a Lewis acid surrounded by ligands, which are molecules or ions, with lone pairs of electrons that serve as Lewis bases. Examples of ligands include water, ammonia, chloride, and cyanide. The strength of complex ion formation is quantified by the formation constant, Kf, which represents the equilibrium constant for the association of the metal ion with ligands. The dissociation constant, Kd, is the equilibrium constant for the reverse process. Large values of Kf indicate stable complexes, as seen in the strong binding of cyanide to transition metal ions. Some systems involve multiple equilibria that share one or more common species. These coupled equilibria often shift the position of solubility equilibria. For instance, the solubility of sparingly soluble salts increases in acidic solutions if the anion of the salt is a weak base that can react with hydronium ions. Calcium carbonate dissolves more readily in acidic conditions because carbonate ions are protonated to form bicarbonate and carbonic acid, shifting the dissolution equilibrium. Similarly, solubility can increase in the presence of ligands that form stable complexes with cations. The dissolution of silver chloride is enhanced in the presence of ammonia because silver ions form the complex ion Ag NH32+, lowering the concentration of free silver ions and driving further dissolution of the solid. The analytical methods used for simpler equilibrium problems, such as writing equilibrium expressions, calculating reaction quotients, and using ICE tables, can also be applied to these more complex systems. By considering all equilibria simultaneously and identifying the dominant processes, predictions can be made about solubility, precipitation, and complex ion formation under a variety of conditions. Chemical and physical processes proceed in the direction that is thermodynamically favorable under given conditions. A process that occurs naturally without the need for continuous external energy is described as spontaneous. Non-spontaneous processes, by contrast, require ongoing energy input to occur. Spontaneity does not necessarily imply rapidity. Some spontaneous processes may proceed extremely slowly. Instead, spontaneity is tied to the redistribution of matter and energy within a system and between the system and its surroundings. Entropy, written as S, is a thermodynamic state function that quantifies the dispersal of energy and matter in a system. Statistically, entropy is related to the number of microstates available to a system, where a microstate represents a specific arrangement of particles and energy. The more microstates available, the higher the entropy. From a thermodynamic standpoint, entropy can also be expressed in terms of heat, transferred reversibly divided by the absolute temperature at which the transfer occurs. Entropy is often described qualitatively as a measure of disorder, though it is more precisely understood as the measure of dispersal. The entropy of a substance depends strongly on its phase. Solids have the lowest entropy because their particles are constrained in fixed positions. Liquids, with greater freedom of motion, have higher entropy, while gases, whose particles move independently through large volumes of space, have the highest entropy. Within the same phase, entropy increases with greater molecular complexity or greater molar mass because more degrees of freedom are available for energy distribution. Entropy also increases with increasing temperature, since higher energy allows access to more microstates. Similarly, dissolving a solute in a solvent typically increases entropy due to the greater dispersal of particles in solution. These principles allow for the qualitative prediction of entropy changes in chemical reactions and phase transitions. The second law of thermodynamics states that any spontaneous process results in an increase in the entropy of the universe. The entropy change of the universe is written as delta S universe, which equals the sum of the entropy change of the system and that of the surroundings. A positive delta S univ indicates a spontaneous process, while a negative delta S univ corresponds to a non-spontaneous process. When delta S univ equals 0, the system is at equilibrium with no net tendency to change. The third law of thermodynamics defines the reference point for entropy. It states that the entropy of a perfect, pure, crystalline solid at absolute zero temperature is exactly zero because only one microstate is possible under those conditions. Standard entropy values for substances at 298 Kelvin can be measured and used to calculate entropy changes for reactions under standard conditions. Gibbs free energy, written as G, is another thermodynamic state function that combines enthalpy, entropy, and temperature to provide a criterion for spontaneity based solely on system properties. It is defined as G equals H minus T times S, where H is enthalpy, T is absolute temperature, and S is entropy. The change in free energy, delta G, determines whether a process is spontaneous. A negative delta G indicates spontaneity under the given conditions, while a positive delta G indicates non-spontaneity. When delta G equals 0, the system is at equilibrium. Free energy changes can be calculated in several ways, including from standard free energy values of formation for reactants and products, from enthalpy and entropy changes, or from equilibrium constants. This makes Gibbs free energy one of the most useful tools in predicting the direction and feasibility of chemical processes. Redox reactions are chemical changes defined by electron transfer, and they are tracked through changes in oxidation numbers of the species involved. In aqueous solutions, redox processes often include water, hydronium ions written as H3O+, or hydroxide ions written as OH-, along with the oxidant and reductant. These reactions can be complex to balance, and the half-reaction method provides a systematic procedure. The method separates the oxidation and reduction half reactions, balances each for mass and charge, and then recombines them to yield the overall balanced redox equation. Electrochemical cells are devices that exploit redox processes. In galvanic cells, a spontaneous redox reaction is harnessed so that electron transfer occurs indirectly. The oxidation half reaction takes place at the anode, and the reduction half reaction takes place at the cathode. Electrons travel through an external circuit from anode to cathode, while ionic charge balance is maintained by ion flow through a salt bridge. A galvanic cell can be represented by a cell schematic, or cell notation, that concisely lists the components of the two half cells and the electrode interface. The property of potential, symbolized as E, quantifies the energy per unit charge associated with a redox process. The potential difference between two half cells is the cell potential, E cell. The standard hydrogen electrode, abbreviated SHE, is defined to have a potential of exactly 0 volts and serves as a universal reference electrode. The potential of any half cell measured relative to the SHE is the electrode potential, EX. Under standard state conditions of 1 bar pressure, 1 molar concentrations, and 298 Kelvin, this value is the standard electrode potential, written as E0X. Larger, more positive standard electrode potentials correspond to stronger oxidizing agents. By combining tabulated half-cell potentials, standard cell potentials, written as E0 cell, can be calculated. A positive value of E cell indicates that the redox process is spontaneous in the forward direction, while a negative value indicates non-spontaneity under those conditions. Cell potential is a thermodynamic quantity closely tied to Gibbs free energy and equilibrium. The maximum electrical work obtainable from a galvanic cell is equal to the change in Gibbs free energy, delta G, for the redox process. The relation between free energy change and cell potential is delta G equals negative N times F times E cell, where N is the number of electrons transferred in the reaction, and F is the Faraday constant. Because Gibbs free energy also relates to the equilibrium constant, K through delta, G0 equals negative R, T natural log K. The standard cell potential is directly connected to the equilibrium position of the redox reaction. Reactions with large positive E0 cell values proceed nearly to completion and have very large equilibrium constants. When conditions are not standard, the Nernst equation describes the dependence of potential on the reaction quotient Q, showing how concentration changes affect the driving force of the reaction. Galvanic cells designed for practical use as power sources are batteries. Primary batteries, or primary cells, are single-use devices that cannot be recharged. Secondary batteries are rechargeable, allowing redox processes to be reversed by applying an external potential. Another related technology is the fuel cell, in which a redox reaction, such as hydrogen combustion, is carried out electrochemically rather than by flame. In a fuel cell, reactants are supplied continuously from external reservoirs, and electrons flow through an external circuit just as in a battery. Fuel cells operate with much higher efficiency than internal combustion engines, since less energy is lost as heat. Electrochemistry is also central to naturally occurring processes such as corrosion. Corrosion is the spontaneous oxidation of metals, with rusting of iron and tarnishing of silver as common examples. Corrosion often occurs because microscopic regions of the metal surface act as galvanic cells, with anodic and cathodic sites separated by moisture and electrolytes. Oxidation occurs at the anodic regions, leading to material degradation. Protective strategies include galvanization, in which the metal is coated with zinc, and cathodic protection, in which a sacrificial anode of a more easily oxidized metal is attached so that it corrodes instead of the protected material. Non-spontaneous redox processes can also be driven by supplying energy from an external power source, a process called electrolysis. In electrolytic cells, a direct current is applied to force a redox reaction to occur in the non-spontaneous direction. Electrolysis is used for refining metals from ores, producing industrial chemicals, and depositing thin coatings of metal onto objects in electroplating. The relationship between current, time, and the amount of substance oxidized or reduced allows quantitative predictions through Faraday's laws of electrolysis, which links the charge passed to the stoichiometric amount of product formed. The representative elements are those in which valence electrons occupy s and p orbitals. These elements occur in groups 1, 2, and 12 through 18 of the periodic table, and they include metals, metalloids, and nonmetals. Group 1, the alkali metals, are extremely reactive, forming cations with a charge of +1. Their ionic compounds are generally soluble in water, and they react vigorously with water to release hydrogen gas and form strongly basic hydroxide solutions. Group 2, the alkaline earth metals, have valence electrons that are more difficult to remove, making them less reactive than Group 1. They characteristically form compounds in which they have a +2 oxidation state. Group 12 elements, zinc, cadmium, and mercury also exhibit the +2 oxidation state, although mercury can form the diatomic cation Hg22+ with an overall charge of +2. Group 13 includes aluminum, gallium, indium, and thallium. Aluminum, gallium, and indium most commonly exist in the +3 oxidation state, while thallium exhibits both +1 and +3 states. Tin and lead in group 14 form stable divalent cations and also covalent compounds, in which they exhibit the +4 state. Representative metals are rarely found in pure form because of their high reactivity. They are extracted from ores using reduction methods. Electrolysis is used for sodium, potassium, and aluminum. Chemical reduction is employed for magnesium, zinc, and tin. The elements that separate metals from nonmetals in the periodic table, boron, silicon, germanium, arsenic, antimony, and tellurium, are known as metalloids. They exhibit both metallic and nonmetallic properties and are structurally similar to nonmetals, but act as semiconductors. Nonmetals differ fundamentally in structure and bonding due to their higher electronegativity and stronger attraction for electrons. Their oxides are generally acid anhydrides that form acidic solutions upon reaction with water. Many nonmetals exist as molecules, and some possess multiple allotropes with distinct physical properties. Hydrogen is unique among the elements. While it shares some similarities with alkali metals, it is generally more nonmetallic in character. With less electronegative elements, it forms ionic hydrides with hydrogen in the -1 oxidation state. With more electronegative nonmetals, it forms covalent compounds where it has a +1 oxidation state. Hydrogen reacts explosively with oxygen, fluorine, and chlorine, more slowly with bromine, and only weakly with iodine, sulfur, and nitrogen. It reduces many metal oxides, provided the metal has a lower reduction potential than chromium, yielding the pure metal and water. Hydrogen halides, when dissolved in water, form acidic solutions. Carbonates of alkali and alkaline earth metals are generally prepared by reacting an oxide or hydroxide with carbon dioxide. Other carbonates form by precipitation. Examples include calcium carbonate, CaCO3, present in limestone and antacids, and sodium hydrogen carbonate, NaHCO3, or baking soda. Carbonates decompose upon heating and react with acids to release carbon dioxide gas. Nitrogen shows oxidation states ranging from -3 to +5. The stability of the nitrogen triple bond makes molecular nitrogen relatively inert, requiring high energy or reactive metals for conversion into nitrides. Nitrogen oxides and nitrogen hydrides are also important chemical species. Phosphorus in group 15 occurs in oxidation states of -3 with active metals and +3 or +5 with nonmetals. Phosphorus is readily oxidized by oxygen and the halogens. Its principal oxides are phosphorus 5 oxide, P4O10, and phosphorus 3 oxide, P4O6. Orthophosphoric acid, H3PO4, is prepared either from reaction of a phosphate with sulfuric acid or by hydration of phosphorus 5 oxide. Orthophosphoric acid is triprotic, capable of forming 3 classes of salts. Oxygen is highly reactive and chemically versatile. Representative metals form oxides, peroxides, and superoxides. Oxides are commonly prepared by heating the hydroxide, nitrate, or carbonate. Peroxides and superoxides form when metals or metal oxides are directly heated in oxygen. Soluble oxides produce hydroxide solutions when dissolved in water. Most metal oxides behave as basic anhydrides, reacting with acids to yield salts and water. Nonmetals, except fluorine, form multiple oxides. Most of these oxides are acid anhydrides. Oxyacid strength increases as the number of oxygen atoms bonded to the central atom increases. The acidity requires that the hydrogen atoms bond to oxygen atoms, rather than directly to the central nonmetal. Sulfur in group 16 reacts with nearly all metals, forming sulfide anions with a charge of 2-. Sulfur also reacts with most nonmetals, generating a wide variety of compounds. The halogens react readily with less electronegative elements to form halides. Metal halides range from ionic to covalent depending on the metal, while halides of nonmetals are covalent. Interhalogen compounds form when different halogens combine. All representative metals react with halogens directly or with hydrohalic acids, such as HF, HCl, HBr, and HI, yielding corresponding metal halides. Noble gases in group 18 are characterized by their low reactivity. They are present in trace amounts in Earth's atmosphere and are used in applications that exploit their inertness, such as protective atmospheres, neon lighting, and refrigeration. While most noble gases are inert, xenon, krypton, and radon can react with fluorine to form compounds, the best studied being xenon fluorides, which serve as precursors to other xenon compounds. Transition metals are the elements located in the D block of the periodic table. Their defining feature is the presence of partially filled d orbitals, either in their elemental form or in common oxidation states. Their reactivity varies widely across the block. Some, such as scandium and iron, are quite reactive, while others, such as platinum and gold, are much less so and are described as nearly inert. The method chosen to extract a transition metal from its ore depends strongly on the concentration of the metal in the mineral and the relative ease or difficulty of reducing the ionic species to the metallic state. In general, metals that are more chemically active require more energy-intensive methods for reduction. In their chemical behavior, transition elements exhibit the typical properties of metals. They oxidize when heated in air, often forming stable oxides. They readily react with halogens to form halide salts. Elements positioned above hydrogen in the activity series react with acids to produce salts and hydrogen gas. Compounds of transition metals in low oxidation states, such as their oxides, hydroxides, and carbonates, usually exhibit basic properties. Their halide salts and other ionic compounds are generally stable in aqueous solution, although in certain cases they require exclusion of oxygen to prevent further reactions. One of the most characteristic features of transition metals is their ability to exist in multiple stable oxidation states, which greatly expands their range of chemical reactivity. A hallmark of transition metal chemistry is the formation of coordination compounds, also called complexes. These species contain a central metal atom or cation bonded to surrounding molecules or ions called ligands. The bonding occurs via coordinate covalent bonds, in which the ligand donates an electron pair to the metal center. Ligands that have more than one donor atom are called polydentate ligands, and they form stable ring-like structures, known as chelates. The geometry of a coordination complex depends on the coordination number, which is the number of donor atoms directly bonded to the metal. A coordination number of 4 leads to either tetrahedral or square planar geometry, while a coordination number of 6 leads to octahedral geometry. In these complexes, isomerism may arise. For example, cis and trans configurations can occur in both octahedral and square planar species. In addition, some octahedral complexes can exist as optical isomers, which are non-superimposable mirror images of one another. Coordination compounds are found in many important contexts, including hemoglobin in blood for oxygen transport, chelating agents for water purification, and pharmaceutical drugs such as cisplatin used in cancer therapy. Crystal field theory provides a simple electrostatic model for understanding the properties of coordination complexes. According to this theory, the negatively charged ligands surrounding a central metal ion interact with the metal d orbitals, altering their relative energies compared to the free ion. This interaction leads to a splitting of the d orbital energies. In octahedral complexes, 3 orbitals form the lower energy T2G set, while 2 orbitals form the higher energy EG set. The energy difference between these sets is called the crystal field splitting energy, often written as delta octahedral. The magnitude of this splitting depends on the identity and arrangement of ligands. Strong field ligands, such as cyanide or carbon monoxide, cause large splitting and lead to low-spin complexes, where the T2G orbitals are filled before electrons occupy the EG orbitals. Weak field ligands, such as halides, cause smaller splitting and produce high-spin complexes, where electrons occupy each orbital singly before pairing. The magnitude of splitting determines many observable properties of coordination compounds, including their magnetic behavior and the vivid colors they display in solution. Organic chemistry is the study of compounds built on the strong and stable bonding between carbon atoms. These bonds allow carbon to form long chains, branched structures, and rings, giving rise to a vast diversity of molecules. The simplest class of organic compounds is the hydrocarbons, which contain only carbon and hydrogen. Alkanes are hydrocarbons in which all carbon-carbon bonds are single bonds, making them saturated hydrocarbons. Alkenes contain at least one carbon-carbon double bond, while alkynes contain at least one carbon-carbon triple bond. Aromatic hydrocarbons are characterized by cyclic ring structures with delocalized pi electron systems, such as benzene, which give them unique stability and reactivity. Organic compounds that are not strictly hydrocarbons can be considered hydrocarbon derivatives. These are formed when one or more hydrogen atoms of a hydrocarbon are replaced by a functional group. A functional group contains at least one atom other than carbon or hydrogen, and it largely determines the chemical properties of the molecule. For example, the hydroxyl group, written as OH, defines alcohols. The ether group, written as ROR, features an oxygen atom bonded to two carbon-containing groups. Several important families of organic compounds are derived from the carbonyl group, which consists of a carbon atom double bonded to an oxygen atom. Aldehydes contain the carbonyl group with at least one hydrogen atom directly attached to the carbonyl carbon. Ketones also contain a carbonyl group, but it is bonded to two carbon groups rather than a hydrogen. Carboxylic acids contain both a carbonyl group and a hydroxyl group on the same carbon, giving the functional group written as COOH. Esters contain a carbonyl carbon bonded to an oxygen atom that is further bonded to another carbon group, written as COOR. All of these compounds feature carbon atoms that are more oxidized relative to the carbon atom of an alcohol group. Nitrogen-containing organic compounds form additional important families. Amines are compounds in which nitrogen is bonded within a hydrocarbon framework. They act as basic functional groups and can be classified as primary, secondary, or tertiary, depending on how many carbon groups are attached to the nitrogen. Amides contain a nitrogen atom bonded to the carbon of a carbonyl group. They may be formed in condensation reactions between amines and carboxylic acids, with the elimination of a water molecule. An atomic nucleus is composed of protons and neutrons, collectively called nucleons. Although the positively charged protons repel one another electrostatically, the nucleus remains stable because of the strong nuclear force, a short-range but very powerful attractive force that binds nucleons together. The mass of a nucleus is always slightly less than the combined mass of its individual protons and neutrons. This difference is the mass defect, which corresponds to the binding energy that holds the nucleus together. The relation between mass defect and binding energy is given by Einstein's mass-energy equivalence equation, written as E equals mc squared. Among all nuclides, only a relatively small fraction are stable. Stability is favored for nuclides with even numbers of protons or neutrons, and for those with so-called magic numbers of nucleons, which correspond to filled nuclear shells. These stable nuclides fall within a narrow band of stability on a plot of proton number versus neutron number. The binding energy per nucleon reaches a maximum near mass number 56, making nuclei around this size the most stable. Nuclei can undergo reactions that alter their proton number, neutron number, or energy state. A variety of particles may participate, including protons, neutrons, positrons, alpha particles, which are helium-4 nuclei, beta particles, which are high-energy electrons, and gamma rays, which are high-energy electromagnetic radiation. Nuclear reactions are balanced in the same sense as chemical reactions. The sum of mass numbers and the sum of charges are conserved. Unstable nuclei with neutron-to-proton ratios outside the band of stability undergo spontaneous radioactive decay. The most common decay modes are alpha emission, beta emission, gamma emission, positron emission, and electron capture. Each decay produces a daughter nuclide with a more stable neutron-to-proton ratio. Some radioactive nuclides decay through a series of steps, called a decay chain, before reaching a stable isotope. Radioactive decay follows first-order kinetics, meaning each radioisotope has a constant half-life, the time required for half of the atoms in a sample to decay. Half-lives span a vast range, from fractions of a second to billions of years, reflecting the broad differences in nuclear stability. These decay properties make radioisotopes valuable in medicine, archaeology, geology, and industry. New nuclides can also be produced artificially by bombarding atoms with particles such as protons, neutrons, or alpha particles. These transmutation reactions can generate both stable and radioactive products. Several elements not found naturally on Earth, such as technetium, astatine, and all transuranium elements, have been produced this way. Two main types of nuclear processes release large amounts of energy. Fission involves the splitting of a heavy nucleus into two or more lighter nuclei, accompanied by the emission of several neutrons. Because these neutrons can trigger further fission events, a self-sustaining chain reaction can occur. This principle underlies both nuclear power generation and nuclear weapons. Fusion, in contrast, involves the combining of light nuclei to form heavier nuclei. Fusion is the source of the sun's energy. Although fusion releases even more energy per mass than fission, achieving controlled fusion on Earth remains technologically difficult and is not yet commercially viable. Radioactive tracers are compounds labeled with radioisotopes that can be tracked to monitor chemical or biological processes. They are widely used in medicine for diagnosis and treatment, in agriculture for pest control, and in industry for safety and quality testing. Nuclear medicine procedures employ radioisotopes with short half-lives to minimize long-term radiation exposure. Radiation therapy uses high-energy radiation, either from external beams or implanted sources, to destroy cancer cells by damaging their DNA. Radiation from both natural and human-made sources constantly surrounds living organisms. Ionizing radiation is the most harmful because it can remove electrons from molecules or break chemical bonds, leading to cell damage. It can generate reactive hydroxyl radicals that disrupt cellular processes. Radiation damage can be somatic, affecting body cells, or genetic, affecting reproductive cells. Rapidly dividing cells are especially vulnerable. Alpha particles have low penetration power, but cause significant damage if inhaled or ingested. Beta particles penetrate further, and gamma rays penetrate the deepest, making them the most difficult to shield against. Radiation detection and measurement employ instruments such as Geiger counters, scintillation detectors, and dosimeters. Several units quantify radiation. Radioactive decay rates are measured in becquerels or curies. Energy absorbed by matter is measured in grays or rads. Biological effects of radiation exposure are expressed in sieverts or REMs. Radiation exposure can produce effects ranging from mild illness to severe injury or death. Protection relies on three principles: shielding with dense materials such as lead, maximizing distance from the source, and minimizing exposure time.